Hello everyone. Today I'll be talking about a very important concept in databases, that is normalization. We all know how much data we handle in real life, whether it's student details, banking records, or online shopping details. If the data is not stored properly, it can become a mess. That's where normalization comes in. So in this presentation, I will explain what normalization is, why we use it, the different types of normal forms, and how it helps in real world. Let's begin. What is normalization? First, let's understand what exactly normalization means. Normalization is the process of organizing data in such a way that it avoids repetition and maintains correctness, or what we call data integrity. When we normalize, we break the data into smaller related tables and make sure there are proper connections between them. This helps us reduce redundancy. That is, we don't want the same data to be stored again and again unnecessarily. Why normalizing a data? So, why do we normalize a database? There are mainly four good reasons. First, to minimize data redundancy. Storing repeated data wastes spaces. Second, to ensure consistency. If the same data is stored on one place and not in another, it creates confusion. Third, to improve query performance. We can retrieve data more efficiently. And finally, it supports better data management, especially when the data grows big. In short, it makes database clean, efficient, and reliable. Next, data anomalies without normalization. Normalization. Now let's say we don't normalize our data. What happens? There are three main problems called anomalies. First is the insertion anomaly. For example, you want to insert a student's contact number, but the table forces you to enter other details like course or address. That's unnecessary. Second is the update anomaly. A student changes their phone number and we have to store in three places. We need to update in all the three places. If we miss even one, it becomes inconsistent. And third one is deletion anomaly. If we delete a student's course info, we might accidentally delete their contact too. To prevent all this, normalization is very useful. Types of normal forms. To solve these issues, we follow a step-by-step process using something called normal forms. These are levels of database optimization. First normal form, second normal form, third normal form, and Boy's code normal form. Each one improves the data structure more than the previous one. First normal form. 1NF is the most basic level. Here we make sure that each column has atomic values, which means only one value per cell, no multiple values. Also, each row must be unique. For example, in a student table, if the phone number field has two numbers separated by commas, that's not atomic. That's a violation of 1NF. Example of 1NF. Let me give you a simple example. Suppose we have a student with this data, name Priya, phone number is 9876543210 and 91235464567889. This is a wrong because the phone field has two values. In 1NF, we split like this. Row 1 Priya's first number and row 2 Priya's second number. Now it follows 1NF, atomic values and better structure. Second normal form. Once a table is in 1NF, we move to second normal form or 2NF. Here we remove what is called partial dependency. This happens when a column depends on only a part of the primary key, especially in tables with composite keys. In 2NF, every non-key column should depend on the whole primary key. Let's see example of 2NF. Let's say we have a table with a composite key, student ID and course ID. Now if the student names depends on only student ID and not course ID, then it is a partial dependency. We fix this by splitting the data. One table for student information and another table for course information. One linking table for enrollment. This makes the student cleaner structure of the table cleaner and follows 2NF. Third normal form. Next comes third normal form or 3NF. Here we remove transitive dependencies. That is, a column should not depend on another non-key column. In simpler words, all non-key fields should depend only on the primary key and not on each other. Next example of 3NF. For example, in a student table, if we have department ID and department name and department name depends on department ID, not directly on student, then it is transitive dependency. To fix this, we create a separate department table with ID and name and connect it to the student table using foreign key. Now the data is in 3NF. Next, Bayes code normal form. BCNF is an advanced version of 3NF. It handles special cases where even 3NF does not fully fix dependency issues. The rule is every determinant must be a candidate key. This ensures no weird or unexpected dependencies remain. It's used mostly when dealing with more complex databases. Next, let's see what are the steps in normalization. To normalize a table, we follow these steps. First, find and remove the repeating groups. Next, ensure atomic values like in 1NF. Remove partial dependencies, that is 2NF. Next, remove transitive dependency, 3NF. And finally, apply BCNF if needed. This way, our data becomes well structured and easy to manage. Next, denormalization when to avoid normalization. Now you may ask, is normalization always the best? Actually, not always. In some cases, like data reporting, analytics, or dashboards, we prefer denormalization. Here, we intentionally keep some redundancy to make queries faster. So, denormalization trades off storage space for performance. Let's break down through normalization versus denormalization. Normalization is best for transactional systems where we insert, update, or delete data frequently. Denormalization is best for analytical systems where we only read data like reports. Some depending on the use case, we choose the best option. Next, let's recap the rules. A short recap. 1NF atomic values. 2NF no partial dependencies. 3NF no transitive dependencies. 3N BCNF determinants must be candidate keys. These rules help us to keep our database structured and correct. Next, let's see use cases, library database. Let's take a simple example, a library database. We have tables for books, authors, and borrowers. Using normalization, we store them in separate related tables instead of combining everything in one. So, updates are easy and we avoid duplication. It's clean, simple, and efficient. Real world application. Normalization is used in many real life systems like banking systems, where transactions and account details must be perfect. Inventory systems, where we manage products, stocks, and orders. University records, where student information, courses, and marks are need to be stored. These systems need reliable and consistent data, which normalization provides. Next, let's see pros and cons of normalization. Pros: it gives efficient storage, it avoids data repetition, and it ensures data integrity. Cons: queries can become more complex, sometimes slower than retrieval, especially in reports. So we have to balance both depending on what we need. Next, we are at the final stage of this presentation, that is the conclusion and key takeaways. To conclude, normalization is a key concept in database design